What's the most used man-made material on Earth? I'll give you the answer. Concrete. This is the Concrete Logic Podcast. Have you ever stopped to think about the sidewalks, driveways, bridges, or the buildings around you? They're all made from concrete. So why don't we discuss it more? In each episode of Concrete Logic, we'll explore a unique concrete-related topic with the help of industry professionals shaping the trade's future. We'll talk with suppliers, contractors, architects, engineers, specialists, and even proponents of competing materials. We'll get their views on concrete and their visions for its future. So get ready to mix things up with Concrete Logic, where we turn the spotlight on the material that's everywhere but often overlooked. This is the Concrete Logic Podcast. And now, here's your host, Seth Tandett.
Welcome to another episode of the Concrete Logic Podcast. And today I have Larry Sutter with me. Larry Sutter's principal engineer for Sutter Engineering, but you probably know him from his work at the Michigan Technological University and the numerous committees he sits on, ASTM, and he's sat on ACI committees as well. Today, Larry is going to share with us how we develop standards and specifications for SCMs, so specifically fly ash and slag, and we may talk about some other materials as well. And that's what we're going to start with. And if it goes to somewhere else, it goes to somewhere else. We'll see. But before we get started, I just want to make sure you all remember how you can support the podcast. There's several things you can do. If you enjoyed today's podcast with Larry, make sure you share the podcast with a coworker or a colleague. That's the first thing you can do. The second thing you can do is if you go to concretelogicpodcast.com, there are two ways to get a hold of me. There's a contact link on the upper right-hand side of the homepage. You click on that. That's like an email. Or you can click on, there's a little microphone icon on the bottom right-hand side of the homepage. You click on that. It's like leaving me a voicemail. And what I'm looking for from you all is topic or guest suggestions. So please reach out and let me know what you want to hear on the podcast. And then the last way on the homepage you can help out is there's a donate button. So if you get some kind of value out of this podcast or any of the other 100 plus episodes that are out there, and you think it's some kind of dollar value, $1, $5, $10, $100, whatever, any amount is appreciated. It helps pay for the things it takes to put out a podcast, and it does cost money. And there's an additional way you can actually support Concrete Logic. We now have a Concrete Logic Academy. Go to www.concretelogicacademy.com. You can join several ways there. There's a network that you can join where we got folks in there that are, it's kind of like a mini LinkedIn. You can do that. We also have courses that we're offering as well, so you can get professional development hours. But essentially what we're doing is we found a way to enhance the podcast experience by adding quizzes to the end of the podcast. So you'll listen to the podcast, then you can take a quiz, and then we can give you professional development hours. So check that out. And with that, Larry, I think that's all my selling for today.
Hopefully I don't have to take a quiz to complete my role here.
No quizzes for you today. We might have you make the quiz.
Oh, there you go.
Yeah, there. Since you've been a professor, I'm sure you've done that a little bit.
A couple times, yeah.
Well, I'm glad we connected, and you agreed to come on the show. So there's a lot of your work has been with SCMs, fly ash and slag, and so I like I was saying, if you could share first how those standards for those two materials are developed, and maybe you were pointing out before we hit record that there's a difference between standards and specifications. So maybe we define that first, and then we talk about how to develop the standards and specifications for each one of those.
Yeah. So maybe just a brief background of how I ever stumbled into this world to begin with. My work previously had been in the area of concrete durability, and anyone who has studied concrete durability in the literature or in their own experimentation has most likely learned that if you want to improve concrete durability, and concrete already is a very durable material, but if you want to improve that durability, the easiest way to do that is through the use of SCMs. The other thing that most people have probably discovered you working with SCMs is variability in properties. You don't always get the same result necessarily. And this whole issue really drove me towards the area of testing and specifications of these materials. I got involved with ASTM. I don't know how long ago it was, probably 25 years ago. And after the first couple of meetings, I started attending the SCM subcommittee meeting and really getting more involved in what they're talking about, because it resonated with me with regards to the other work I'd already been doing in concrete durability, that there was actually something here of value to be attained. There was improvements that could be made in the tests and in the specifications. And so I guess I saw an opportunity or a need, however we want to look at it, to try to contribute in that area. So that's how I got there. As we were talking at the beginning, and I'm guilty of this, I do it, but I try not to do it. The term standard gets tossed around very loosely. And right now we have a lot of people coming into our industry who are not necessarily concrete people, who are looking to improve concrete, particularly the carbon footprint of concrete. And you hear this word used a lot, and they use standard and specification interchangeably. A standard is simply a document that has been developed under a consensus process, a document that we all agree on. And consensus doesn't mean that it's the best, it means it's the lowest common denominator. We've reached something we all can agree on. A standard could be a specification for a material, it could be a test method, it could be a practice, it could be a guide, it could be a lot of different things. But a standard basically is a document that we as an industry have all agreed upon. It's been developed in a consensus process where we've had representation from all aspects, all stakeholders, and we've reached agreement on what that document should say, and we call it a standard. And ASTM is the principal developer, the source of standards in the U.S. for the construction industry. The other major source of standards is AASHTO, American Association of State Highway Transportation Officials. Those standards are primarily used in transportation construction, but between those two, they cover probably 95, if not more, of the national standards. There clearly are specifications and test methods developed locally at the DOT level or even at lower levels. You can argue whether those are or not standards. I think it depends on how they're developed. But a standard is generally is a document that is accepted by anyone who's subscribing to it as being, we're in agreement that is the document we're going to work from. A specification is another term that gets misused a lot, or I shouldn't say gets misused, it gets misunderstood. And I think probably my colleagues in academia are as more guilty of this than anyone. That is thinking that a specification is going to be a textbook, or it's going to be a research paper, or it's going to be something that's going to provide some sort of source of enlightenment to the user on how to use that material. And it's not. A specification is the basis of a contract between the buyer and the seller. Mm-hmm. A specification tells the buyer what to expect or how to measure that material. And then the specification tells the producer what they have to do to produce that material. And therein lies the issue of variability. When we start talking about variability in materials and performance of materials, the question always comes back to, are we measuring the right things in our specifications? Are we measuring the right properties? And if we are measuring the right properties, are we setting limits or boundaries on those properties that are both attainable by the producer and make sense to the user from a standpoint of how the concrete's going to vary as it properly varies. So that's really the challenge of writing specifications, is trying to understand that it's not a scientific paper, but at the same time, you need to base what you're doing on science. You need to have test methods that are agreed upon, hence their standard test methods. Those test methods have to have known precision and bias, so we can understand what the variability is in the result. And we set limits on certain properties, and we set limits on properties that matter, and we don't set limits on properties that don't matter. We still may measure them because they might be of interest, but we don't set a limit on things that don't matter. And you put all that in a bag and shake it up and dump it out on the table, and that's the makings of a specification.
Uh-huh. So can we talk a little bit about, I guess, the standards for, well, we could start with fly ash. I guess there's on previous podcasts we talk about class F fly ash, and I guess that's the dominant material right now. Is that true?
Fly ash is still the predominant material we're using as an SCM in concrete.
Mm-hmm.
I assume your listeners know the term SCM. It stands for supplementary cementitious material, mm-hmm. which means we use it as either a replacement or an addition to the cement component of the concrete, typically Portland cement, but not necessarily Portland cement. So fly ash is, probably 2/3, from the numbers I've seen recently, probably 2/3 of the total SCM use still in the United States is fly ash. Fly ash is a very interesting material. I believe it was 1937 that Davis published the seminal paper on fly ash use in concrete. And if you go back and read that paper, pretty much anything you need to know about fly ash, they covered in that paper. I don't think there's been a lot new developed. I mean, there's been some new developed, obviously, but that paper was just amazing in its how comprehensive it was. The first specification for fly ash, to my knowledge, was ASTM T350, which was published in 1954. And there, when you look at those two documents, Davis's paper, which was very scientific and in-depth and rigorous, and you look at the specification, you start to see certainly the difference between what a specification and the scientific paper is, but also the role of a specification or the perceived role of a specification in industry. When T350 was written, fly ash was treated as sand. It wasn't considered part of the cementitious material in concrete. And there's a lot of reasons why that probably was the case. And most of them are economic or market driven. They're not driven by science. Mm-hmm. And conversely, as a result, the specification for fly ash evolved from that standpoint. We're using it not as a cement replacement, but as a sand replacement or as an addition to sand. Fly ash was inexpensive when it first came out, so although it was used as a sand replacement, people learned pretty quickly to use it to replace cement. And before long, we stumbled over the fact that it actually improved the durability of concrete. And that started us down the path, nearly 100 years ago, of fly ash use. And fly ash is abundant. It's been used. It's been, coal-fired power was our mainstay up until 10 years ago, 15 years ago. And so it was always there. It was inexpensive. It worked. And it just grew and just took over the market. The standard currently, C618, ASTM C618, Asheville M295, are the specifications for fly ash, and they still have elements in those documents that date back to 1954. You can still find verbiage, you can still find tests, you can still find the limits that were set back when we didn't even really know how to use the material. Now we know how to use the material. We know it's a replacement for cement. We know the benefits of it, and so the tests that we need are evolving. Whereas before we were just mainly worried about fly ash doing no harm, we developed tests like the strength activity index test, which is actually a fairly recent addition to the specification. It was added in the 1960s, I believe, early 1970s. We used that for many years as a way of trying to measure strength contribution, and what we know from research and from experience is that in many cases it doesn't tell us anything about strength contribution. And so you started by talking about Class F ash in particular. Class F ash is a very slowly reacting material, and you get strength at a much later time period in the concrete life. And so the strength activity index, we're measuring strength contribution in 7 days. Basically, we're looking for it to do no harm in that test. And if we let that test run out longer, we can maybe see the contribution. But who wants to wait 28 or 56 days for a test result? Not too many people. So the whole issue of measuring the reactivity of the material has emerged, and new tests have been developed. ASTM has developed a new test method based on research that was done in Europe under the RILEM program, and those are referred to as the R3 tests for measuring the reactivity material. They measure the heat evolution from the reaction of the material, or else they measure the amount of water bound in the chemical reaction with the material, and it's called the bound water test. And this is an emerging test now that's been standardized. It is a standard test. And it is now, we're starting to inch it into our specifications, trying to figure out how to use it in our specifications. And there's many challenges to that. I mean, number one is what are the limits and what do they mean? But then number two is, even if we can decide on what the limits are, what they mean, as a user, what do you do with it?
Mm-hmm.
So if I tell you that I have a bound water content of 5 grams per 100 grams of cementitious material, a ready-mix producer is going to go, so what do I do with that number? So it comes back to trial batching, beginning experience with the material, understanding how the material works, and then going back to your other point you made earlier, the consistency. It comes back to the point of, if the number 5 works for me and I get the ready with my mixed design, I can get the performance I'm looking for, then how consistent is that number 5? And what kind of variability is going to make a difference? Is a 4 going to be a problem? Can I go down to 3? What kind of variability in that number, whatever that number is, can I tolerate? And what does it mean if it varies? That comes from experience on the user end. And we can't necessarily look at our specifications to provide that answer. We have to rely to some extent on the user, to a great extent, on the user community to become familiar with these tests and these materials and understand how to use them. And as we evolve new specifications, this is the biggest challenge, trying to go away from something we've done for 100 years towards something new that is completely different, that we don't really necessarily have the experience with, and trying to figure out how to make concrete with it.
Yeah. I just wanted to back up to your comment. How did they determine that including fly ash in concrete, it makes concrete more durable? How was that discovered?
That was some other work that followed on from, well, I guess we need to kind of qualify that. The first thing that was discovered was that fly ash was a way to mitigate alkali silica reactivity. And Stanton was the person who published that. I believe Stanton worked for the California Department of Roads, I believe it was at that time, now Caltrans. He had ASR issues with bridges, and through research, he determined that adding fly ash would mitigate the ASR problem. And that was really the first thing we realized. And so I kind of made a offhand comment about, Davis's paper pretty much told us everything. And to a great extent, it did. But what we have really spent a lot of time on since then is understanding the mechanisms of how does fly ash improve durability, and how does fly ash mitigate ASR. And what we've learned is that there's some chemical reactions that help mitigate ASR specifically, but there's some general reactions where the fly ash or the SCM, I don't want to just focus on fly ash, SCMs in general, reduce the permeability of the concrete. And back to my professor days, I always tell the students that, any bad thing that happens to concrete involves water. So if you can keep the water out of concrete, you can go a long ways towards improving the durability. And that's what SCMs do for us, is they reduce the permeability of concrete. So water cannot ingress. And that just pretty much shuts down every bad thing that can happen, whether it's sulfate attack, whether it's de-icer attack, whether it's ASR. Removing that water is a big thing. And understanding the permeability impacts of SCMs on permeability is that, in my opinion, it's at the heart of really understanding how SCMs contribute. Mm-hmm. And that's another area where tests are being developed, research is being done, methodologies for measuring bulk resistivity, other things like that nature, to try to assess the impact of SCMs on permeability. It's really the key thing I think we've learned beyond what Stanton told us, and he touched on permeability in his work. But the past 50 years, we've really come to a much better understanding of how that happens and why that happens, and how to use materials to achieve that.
So using fly ash, it allows the water that's in the mix to disperse, I guess, more efficiently. Is that what I'm hearing?
So cement, when it hydrates, forms a porous structure.
Okay.
And hardened cement is really a mixture of two things: calcium silicate hydrate and calcium hydroxide. And the calcium hydroxide is soluble in water. And so the net result is you have a porous structure, and you have one component of it that's soluble. And so water can infiltrate to begin with. Depending on the conditions, that calcium hydroxide may dissolve. And so what we'd really like to do is plug up that pore structure. Mm-hmm. What pozzolans do, like a class F fly ash or a silica fume, is they chemically react with that calcium hydroxide and form more calcium silicate hydrate, or CSH, and it plugs up the holes.
Okay.
And that's really what happens in any SCM, is that you get a chemical reaction that produces more CSH, reduces the pores between the CSH in the cement matrix, and it decreases the water ingress or any sort of fluid ingress into the concrete. So it's really a matter of producing more of the good stuff and eating up some of the bad stuff.
Okay. Understand that. So the new test method that you mentioned, it was called R3, is that right?
The actual test method is ASTM-C 1897, and it has a much longer title. I'd have to pull it up to recite it to you, but it basically is isothermal measurement of reactivity based on isothermal calorimetry and bound water measurements, and I don't have the exact title right, but it's of that nature. The R3 is kind of a term that was coined by the RILAM people. RILAM is a research organization in Europe, and they coined the term R3 as rapid, reliable, and reproducible. And so in their publication, they started calling it the R3 test, and that has caught on in the vernacular. You hear a lot of people talk about the R3 test. They're talking about ASTM-C 1897, a standard test method.
Okay. And was that test method used on other material, or how, I mean,
It's
or
been
did
used primarily it's been used only for evaluating SCMs, but a wide range of SCMs, fly ash, slags, natural pozzolans, calcined clay, silica fume, and some other industrial byproducts. There was an extensive body of literature out there on using these tests in a variety of materials. The majority of the work has been done with fly ash, calcined clay, natural pozzolans, and slags.
Mm-hmm. So they found I guess what the ideal fly ash.
But again, the test method just tells you the property, it tells you the reactivity of the material. So if you put it in the presence of a calcium hydroxide solution, going back to this idea that SCMs react with calcium hydroxide, if you put this material in the presence of a calcium hydroxide solution, it's going to react. And we measure the extent of that chemical reaction. We measure that extent by measuring the heat that's given off by the chemical reaction, or by measuring the amount of water that is bound. So this calcium silicate hydrate I mentioned is calcium, silicon, and water combined to make a mineral. And so if you're going to take calcium and silicon and water and make a mineral from a solution, the water is going to disappear. The water is going to get bound up in solids. And that's what we measure when we measure the bound water. How much water from the solution that you put into the test was consumed making a new solid.
Okay. I was just curious if it was a test that, was used on another material and someone's like, oh, we can use it on fly ash as well, or if they were like, okay, this fly ash we're really happy with, this is the standard and this is how it reacts in this test. So that's the standard that we're setting for all fly ash. It has to do like this ideal fly ash.
Yeah, there is. That would be really wonderful if we could do that. I mean, there is no such thing as an ideal fly ash. There's no such thing as an ideal Portland cement. All these materials. This is what we live with every day. Is that every material we work with, including the rock for that matter. I was going to say except the rock, but really including every material we work with for making concrete varies. We don't have a luxury of the steel industry where they can make the material, out to the second decimal place. It's always going to be the same, or plastics for that matter. Our material varies. It varies day to day. It varies job to job. It varies by location, and we have to live with that. We can't ever. That's not going to go away. It will never change. We have to learn how to live with it. So the question here is, how do I measure what it is? So that's what the test tells us, is what is the reactivity. It gives us a number. As I said earlier, it might tell you have 5 grams of bound water, or it might say you have 160 joules of heat evolution per gram of this material. So that's a number we can measure the quality of the material by. What that number means is a whole different story. We have to start then correlating our experience with measuring that number and getting that number with making concrete and how the concrete performs. And generally speaking, as the reactivity increases, meaning we get more bound water or we get more heat evolution, as that increases, you're going to get more strength development per pound of material. You're going to get more development of other phases that are going to fill those voids and reduce the permeability. So generally speaking, as the number increases, the performance of the material is going to get better. And I want to emphasize, generally speaking, because there's many, many, many caveats. We can spend 3 more podcasts talking about the caveats on that statement. But generally speaking, that's true. A higher number is better. The question then becomes, okay, fine, I got a higher number. And in many markets, you don't have a choice. It's not like you got 15 fly ashes to pick from and you're going to go pick the one with the highest number. You're going to take the one you have available to you at the right price. The question is then, how is that number going to vary? Once I've developed my mix design and I have a certain level of reactivity in that material, how is that number going to vary? And then what does that variance mean on my performance of my concrete?
Mm-hmm.
That comes from experience with the mix design and making the concrete, testing the concrete, making the measurement, understanding the variability of the measurement, making the concrete, and looking at the effect of the variability on the concrete. That's the step. And frankly, that's a step that we should have been doing with a fly ash 50 years ago. We never did it. We just said, give me a class F, give me a class C, put it in there and see what's going to work. And we had problems because it varied. Not all class Fs are, not all, no class F ash is the same as the other one. No class C ash is the same as another class C. They are not interchangeable parts. So we can't, and we just always went down the road of assuming they were interchangeable parts. I could just drop in any ash and life was going to be good. And we had problems. And we historically have had problems with variability. Everyone talks about variability in these materials. Well, as I said earlier, newsflash, these materials are going to vary until the day we all die. It's not going to go away. We have to learn how to live with that variability, measure that variability, and predict what the result of that variability is going to be on my concrete performance. And that's on us as concrete engineers using the material to understand how to work with that material and what the variability of that material means. And the best thing we can do as an industry is try to get the best tests we can to measure that variability. And that's where we're really trying to work on the ASTM, getting the best tests to measure that variability. But that's only the starting point. From there, you got to make concrete and see what happens.
So it's more to verify what you have, so you know what to do within the mix design to work with what you have. It's not, hey, this is good. This is good fly ash. No, it's okay.
There's no good or bad. It's what it is, and then how is it varying? Mm-hmm. And those are the two key things that we want to know.
So I guess my next question, it may be, I can already hear the answer. It varies, but so the use of fly ash or any SCM is to offset the amount of the cement that you're using. And there's various reasons to do that. When at one point in my career, it was to use it to reduce the cost of concrete, and that's no longer the fact. Now it's to reduce the what we're calling the carbon footprint. So
and improve the durability.
Yeah. Okay, so that leads me to my next question. At what point are you putting too much SCM in your mix?
When you no longer improve the durability, I guess, or it becomes cost ineffective. There's obviously, we all know there's other things that affect concrete, or other things we're concerned about with concrete, I should say, such as workability, placeability, strength development. How rapid am I going to get my the needed strength? Many other properties. So, for example, you could go to a very high replacement of a material like a Class F ash, for example, in a mix, and long term it may be more durable, and from a carbon footprint perspective, it's probably a step forward. It would be a step forward, but if all of a sudden your schedule now is going to be increased because you can't move the forms because you're not gaining strength, there's an economic hit on the contractor or the owner or both, and you got to live with that. So you're going to say, I can't live with that. I can't live with that impact on my schedule. So I'm going to back off on the fly ash. I'm going to use less. I'm going to get my strength quicker. It's a trade-off of many, many, many variables. There isn't necessarily a right or wrong answer. You got to look at all the various variables that are out there and try to come to a conclusion on what is the best answer.
Mm-hmm. Yeah.
This is probably a role for that infamous artificial intelligence, but it's and it is being looked at for this purpose because it is a multifaceted issue.
Mm-hmm. Yeah. Yeah. Like you said, it depends. It varies on where you're at and your mix design and everything.
I'm a big fan of SCMs. I've seen all the benefits. I've seen the downside too, but I've seen the benefits. And so, my first instinct would be to answer your question by saying as much as possible.
Yeah.
And I think I'd probably stick with that answer, but define what I mean, which I just tried to do by saying as much as possible. I mean, if you start increasing the SCM content to the point where you start sacrificing other aspects of the material, then you have to start asking yourself, is that worthwhile?
Mm-hmm. Do you agree with specifications that put a cap on your SCM use?
No.
No. Okay.
No.
Because I've seen them like cap it at 40 or 50%.
Yeah, that wouldn't be so bad. I've seen caps of like 15%. I mean,
right.
And 40 or 50 you probably could live with, but no. I mean, that's another aspect of it. As we move forward towards low carbon concrete, we have to get out of this mindset that we're going to limit things because the materials that are available, all the other aspects of the job have to be considered. Many times there's things that we can do that we can't get there because of the limits that are put on us in the specifications. Minimum cement contents, for example, and then, like you say, maximum SCM contents. You just restrict the ready mix producer or the concrete producer in terms of what they can actually do. And many cases, the limits are not a hindrance, but in many cases, the limits are a hindrance. It just ties their hands and limits how many options they have to try to achieve the other aspects of the project, which may be carbon reduction, which may be rapid construction, or a number of different things.
Yeah. So if I was to guess, you're a fan of performance specifications versus prescriptive. We had Colin Lobo on the podcast recently. We did a whole podcast on performance versus prescriptive.
I think everyone's in favor of performance-based specifications until you get to the point of trying to define what performance means. Then all of a sudden you have an issue of maybe a lack of a meeting of the minds in some cases. So measuring performance, where do you measure it? How do you measure it? What is it? These are all things that have to be defined. I mean, without a doubt, performance specifications are the way to go. And it's something, again, you hear a lot of people who are coming to our industry trying to achieve carbon reduction who don't know our industry. They start throwing this out as if it's a very simple solution, and it's far from a simple solution. It's something that's been talked about for as long as I've been in the industry. And it's not easy to achieve because we don't know what it is, how to measure it, where to measure it. And so there's many, many aspects to it. But anything we can do to move towards measuring performance and move away from prescription, in my opinion, is a good thing if we can achieve it. The question is, what is it and how do we do it?
Yeah. In your work with SCMs and the effort of carbon neutrality, has anyone raised a question about the carbon footprint of producing a fly ash or a slag during its production? Well,
yes. And again, that's probably a whole nother podcast. And so we're in this world now living with EPDs, environmental product declarations for materials. The environmental product declaration for any given material is based upon a product category rule, PCR. And that product category rule draws the boundaries around where we measure energy and other inputs and where we don't measure those.
Right.
And you can argue over what the PCR is or isn't, but the PCRs are defined for SCMs, and that's how we measure the energy input. So it's a very controversial issue. I think there are some, particularly on the power production side of the business, who would like to see maybe more of the environmental impact of coal combustion assigned to the fly ash and not to the production of power. Whereas those of us on the concrete side who are using this material say, well, it's a waste material. If we weren't here helping you take it away, not only would you wouldn't have any option. It'd just be increasing your carbon footprint. because you'd be wasting this material. So we're doing you a favor. And that's euphemistically saying it. But the point is, drawing that boundary is never simple. And it's something that I hopefully won't ever be involved with. I just live with it. Someone else defines it, and I'm not going to throw any stones at it. The PCRs and APDs are what they are. It's people who spend their life understanding how to do this and what's right, what's wrong, and I'm just going to use them and just make concrete.
Right. Well, I appreciate you using the term energy use versus the carbon footprint. I can get on board with that versus
that's where the carbon footprint comes from. Obviously, is from the energy use. So,
well, it's obvious to folks like you, but I don't think it's obvious to everyone out there.
No, that's probably true. Yeah.
Well, this was great, Larry. I appreciate it. I think we covered a lot today, and if you hopefully you liked doing this, and we'll bring you back on. We can talk about those other things that you said you can make 3 podcasts out of. I'll keep you that.
Well, yeah, there's a lot of depth to this area.
Yeah.
I'll just say one other thing while we're talking about specifications is ASCM, we are developing what we're referring to as a performance-based specification for SCMs. And it's really, the intent of this was really to deal with the emerging materials. We've talked, pretty much exclusively about fly ash, and we've hinted at slags and other materials, natural pozzolans, and they're there and they're very important, and their uses of steady or increasing. But there's also a lot of emerging materials coming out, and if we go back historically, we can do what we did, which is define a spec for fly ash, define a spec for slag, define a spec for silica fume, and then end up with a book full of specifications. Or we can just take a step back and say what you said earlier is performance. What we really want to know in the end is, how is this material going to perform? We want to measure key factors such as reactivity, and we want to understand the variability in those. So that's really kind of the philosophy behind this specification we're developing for SCMs, is to measure the key things, limit a few of them, and report the rest, and give the concrete producer the information they need to start engineering concrete using these new materials. It's going to be a paradigm change, and everyone involved understands that, but we have to take the first step somewhere, and we're very close to having that specification done. When it is done, in theory, that one specification could be used to specify any SCM. In practice, it's going to be used for the emerging materials. Maybe with time, the existing materials like fly ash and slag and so on will migrate to that same specification. But we're trying to move down that road of measuring performance and reporting it and giving the concrete producer information to make informed decisions on how they design their material. So that standard is under development, and hopefully within the next 6 months, it's going to be developed and approved and moved towards publication.
Cool. Well, we'll look forward to that, and it'll be something else for us to discuss on the podcast. If folks want to reach out to you, Larry, what's the best way? What's your preferred way?
Email is the easiest. Sutter.engineering@gmail.com. Okay.
All right. I'll put that in the show notes so folks can reach out to Larry. Larry, thank you for coming on the show today. I appreciate it. And folks, until next time, let's keep it concrete.
Thanks for joining us for another episode of the Concrete Logic Podcast. If you got value from the show, here's how you can provide value back to support the show. Visit concretelogicpodcast.com and click the donate button to send value back. All dollar amounts are truly appreciated. And now, to close out the show, here's Mike Dunton.
Ring, ring, that alarm always sings couple hours before the sun comes up. light, put some diesel in the lights and wait till the trucks roll up. Yeah, this ain't how most folks live their lives, dripping in sweat, working overtime. But while they're tying their ties for their 9 to 5s, we're out here changing these skylines with wood, iron, and mud. We work hard for $1, give thanks to the Lord above. Never make a man do something you can't prove. Hard work calls for a drink or two. Expect more, it's written in our blood. With wood, iron, and mud. From the swamps to the city, from the Lone Star heat to the woods of the Georgia pine. Good old boys and girls who ain't afraid of getting dirty for a clean time. And if you want to see the fire in a grown man's eyes beneath the hot summer sun, find the wild-eyed boys clocking days and nights, working hard to get that job done with wood, iron, and mud. We work hard for $1, give thanks to the Lord above. The color of our collars ain't white or blue, we're all gray collar through and through. Expect more, it's written in our blood. With wood, iron, and mud. With wood, iron, and mud. We work hard for $1, give thanks to the Lord above. Never make a man do something you can't prove.